That's good to see. As you can see, I completed my homework. It's not due tonight. It's not due till Monday, but this is what your homework will look like so that you can kind of, in your mind, make a reference of the picture. Remember, the ATmega 328P is producing hex digits between 00 up to 7F, and then from 7F down to 00 again. So when it's all the way at the bottom here, it's 0. When it's at the top, it's 127. I did what I told you to do, which is right after class on Monday night, I just wrote it and got done with it. I hadn't written it before, so I just went ahead and did it to make sure it wasn't a hard assignment. So this is due, well, at least the processing piece. The other parts I don't want. But the processing code is going to be due to me at the start of class on Monday, and I'll tell you how I'm going to collect it then. Anybody have any questions or any more things we should talk about that assignment? Okay, well, let me close it down then. I think what I want to start with tonight is I want to go through the instruction set. So it's very clear when and why you would use one of the particular instructions. That I think you're going to find that to be very useful to know. And some of it you have to kind of put in the back of your head somewhere so that you can pull it out when you need to. If I gave you on the final some snippet of code that was broken because the instruction's the wrong instruction, you should be able to do that. I assume you saw the announcement that I just posted that the final exam is on the 20th of December. That's, when is that? We have one more week and then the final. Next week on Monday, which is the 13th, we're going to probably together write a piece of ATmega code that's a little harder than what we've been doing. And then on Wednesday next week, which is the 15th, I think I'm going to do a review. It'll have some little bit of new material, but mostly focused at making sure everybody that wants to will be able to complete the class correctly. Some of you, I'm pretty sure I'm going to see again. But those of you that are going to get the higher grades and things may want to just do a little review so you can be the guy or the girl that gets the highest score in the class. And so next week on Monday we'll do just a development session, and then on Wednesday we'll do a review of all the material in the class. And I don't know how long it'll last. Might not be the whole class period, might be a little bit longer, but we'll make sure that we at least address any questions you have at that point. And then the 20th, which is the Monday after that, is the final exam for this class. And it'll be during class time. Of course, if you have an accommodation, you'll have the extension afterwards. Anybody have any questions about those dates? I would ask you now, give me a green circle if you think you're going to get an A on the final exam. I would have thought most of you would get an A. If you've been paying attention, even if you haven't been participating, assuming you've been taking good notes, I don't see why you wouldn't do well on the exam. Now, you may not get a good grade for the class if you didn't participate, because let's look at that again. It's been a while since I visited this. Yeah, the homework assignments we've been turning in, plus your participation is half of your grade. So if every night you have not contributed, your hand never goes up when a question is asked, or when I call on you, you never know the answers, then you're not really participating or being part of the labs. And some of you have just simply not turned in homework. You've turned in maybe something that was what I gave you. Maybe if I gave you a piece of paper and said, do something with this, you gave me back the piece of paper. So a lot of you will be losing a lot of points here. A lot of you have gotten a lot of points here, though, because you've really participated well. Some of you have really, really outdone yourself. And I really appreciate that in a class like this. The first two exams count for 20% of your grade, and then the final exam itself is 30%. So you can, as you can see, you want to do well. Participation-wise, it's a little late to get going, but we still got a couple classes. But for the final exam, definitely you want to do as well as you can on that. And I'm assuming that's what some of you have been counting on, is you don't do well in participation, you do well here, your grade can't be that bad. Well, we'll see. Anybody have any question about the grading? Okay. Well, make sure you get that homework done and that it's working for Monday. That, is part of this first section up here. So even if you haven't been participating, this will boost a few more points on you if you do things like get that right and it's working. In the homework, you can share discussions about it. You just can't share code. So you can't copy somebody else's and turn it in. Okay, well, let me put that aside. What's this? Okay, let's take a look at the instruction set. Okay, if you want to follow along with this, I'm in the data sheet. I'm going down the left side until I find instructions. Section 37. It's on page 625 in my book. Okay. Although most of these are instructions, you could kind of intuitively know how they work. I think it's still a good idea for us to make at least a pass over it so that if you're asked to write some code soon, they'll be fresh in your mind. So they're divided into sections, and in the section which is titled here Arithmetic and Logic Instructions, or Arithmetic and Logic Instructions, if you want to talk about an ALU, we have two versions of an 8-bit add. We have one that's add, where we take source register, write it into or add it to a destination register without regard to carry. Carry is not taken into consideration. Then we have an add with carry, which takes a source register plus carry and adds it to a destination register. Now you might wonder, where would you use one over the other? And let me see, do I have that here somewhere? The idea would be, I have a couple numbers. I have, a couple of more numbers that should be lined up. I didn't line them up. When I add this column here, I don't care about carry. So I would be adding using the add instruction. So 6 and 4 is 10, but it does produce a carry. So the second column does care and would use the ADC instruction. So if you could envision on our machine, let's say we had 4 registers. And we'll just make up numbers for them for now. This is R4. Well, actually, let's make this R5, R6, R7, and R8. We want to add up two 16-bit numbers. So the first number we're going to put into this pair of registers, and the second we're going to put into that pair of registers. Now, because in the registers when we work on these, if we take as our guide R29 and R30, for example, which is called the Z register, we would treat these the same. The low part of our number goes here. The high part of our number goes here. Low part here, high part here. So let's assume for a second that the register's low part is 03. The register's high part is 42. And I'm writing in hex. This has an A3. This is a 2, 1. So in terms of the addition problem we're actually doing, we're taking the number in 16 bits, 4203, and we're adding it to 21A3. Now let's actually, I'm going to change this for a second. Instead of this being a thing, I'm going to make it be a 7. So it's going to be 4273 added to 21A3. Now, when we do the addition for this problem, we're going to add, first of all, that pair together. And the answer is going to replace the two numbers that are, or the number that's here. Then we're going to take and add the second two numbers, which are the first two, and they will replace those two, the sum will replace the starting register. So just to look at this happen, we know this guy does not have a carry coming in. So there'd be an add of those two. So for example, we might say add to R5 whatever's in R7. And so we get a 6. We get 10 and 7 is a 17, so that's a 1. Carry the 1. So carry bit has been set to a 1. Now that means that this register, of course, now no longer contains the 16. I'm sorry, the 73. It now contains a 16. Now we're going to add the other two together with the carry. So 1 plus 2 is 3 plus 1 is 4. Carry the 1 is 5, 6, 7. So it's going to be a 7, 4, which is going to ultimately wind up here. To get that to happen, though, we couldn't use an add instruction. We have to use the add with carry. And we'll be adding to R6 whatever's in R8. Of course, when we're done, our final number here is 7416, which is the answer we need. Robert, you have a question?
Wouldn't it be 6416 because we carried the 1 to the 2 and 1, and then we're adding 4 and 2, correct?
Yeah, I just added wrong.
Okay.
This line going there, I thought it was a 3. Mikhail, your question?
Yeah, so for when you add register 5 and register 7, right? Why is 7 and 8 equal to 1 with a k bit of 1 instead of 7 with a k bit of 1?
When we're adding registers.
5 and 7.
Well, we're at 5 and 7. So 5 is at 7-3. 7's an A3, right? A3 was a 7-3. We're adding together the low parts of the two 16-bit numbers. One of the numbers is 4273, the other is 21A3. That make sense?
Yeah.
Okay. Robert, do you have another question?
No, I have a clarification for what I think Mikkel's asking.
Okay.
So A is 10, Mikkel, and 7 plus 10 is 17. But in hexadecimal, a 10 actually equals, or F is 15. So you would carry the 1 because you've gone to 16, and then you have 1 as well. So it's 16 and 1 is how you'd represent 17.
All right, so the number 17 in decimal is equal to that in hex. Okay, but this is why we would use an add and an add carry. Now, the question becomes, is that a legal pair of instructions? How would we find that out? I mean, we clearly see them written here. We see they have two registers. But what we don't know is, are there any restrictions on these registers, for these instructions? So we would go to our instruction manual. Actually do this. We'd find add. It'll be all over the place in here. On page 24. And we would verify here that the registers on both the source and the destination can be coded as register 0 through register 31. Some instructions, this is limited. You don't have enough bits to be able to do that. And add with carry, I believe, is right in front of it. And add with carry also allows us to use any of the 32 registers. Now, when we have an instruction, for example, like add, one of the things we might be asked about is, what flags does it affect? Over here is a list of all the flags that could be affected by it. Additionally, the number of clocks it takes is represented over here. So although it takes more t-states than that, because of buffering, this can complete in a single t-state. Then this is a general picture of what the instruction does. It's not always complete because they don't really have enough space here for it. But for the two instructions we did, it says take the source register, add it to the destination register, put the answer in the destination register. This guy includes carry as well. Now that's elaborated on over here. Here's the same operation. In this case, they'll be identical because it's very to the point. It tells you also what happens to the program counter. Tells you how you would encode it. Then indicates which flags will be set. And here are the Boolean expressions under which those flags get set. So for example, the 0 flag is set if all the bits are ANDed together and there's still a 0. And then they give you a little English language sometimes to be necessary. They always encode things differently in different books using logic. The little upper pointing arrow means AND in the case right here. This is an exclusive OR. I don't see any ORs on this page. And then the inversions are indicated by having a not sign or a bar over the top. Additionally, they'll usually give you an example. Here again, they're taking R1, R0 plus R3 and R2, and they're adding them up very much the same way we did, and then add with carry for the leftmost byte or the high byte. It takes one instruction word, which happens to be 2 bytes. Remember, we needed to know how big a program counter was. It always advances in words. And then the only other thing that's in here really is which architecture is our processor chip. Now, we're really an architecture called AVREX. Let's prove that to ourselves, and then we'll figure out how we would use this. In this document, we search for ATmega 328 B. We'll see that we are an AVR E plus. Oh, I guess I said X, it's E plus. We're exactly the same as a different family, except we don't have these 3 instructions. Now, if we look back at the beginning of this section, do they explain it here? Let's go actually back to the very top. There we go. So AVRE is an AVR instruction, which is the same as the original set, which was AVR, plus it added move W and the load programming memory instruction. You got better. However, if you're a plus, which we are, they also added a series of multiply instructions. But they say we're exactly the same timing-wise as the AVRE. Now, when we were looking back at the add instruction, I still have this on my list. We saw on the table one of the choices is AVRE. So the timing we would use would be the one. If there is no AVRE plus, we would use AVRE. And if there was no AVRE, we would use AVR. We're definitely not any of those 3. And in most cases, they're going to be the same anyway. But just so you're very clear about how to use this document, because this is kind of the Bible of these instructions. Okay, let's look ahead. Now we have an instruction which takes and adds a constant value, that's the I, an immediate variable, to a word. So this itself is a 16-bit instruction. It affects a slightly different set of flags. It does S instead of H. Takes longer to execute, but it does 16 bits at a time. Again, we have source and destination registers. Well, actually, in this case, we have a destination register to which we're going to add an immediate operand. So there is no source register because this is where the result will wind up. Again, we can look it up, ADIW. And we'll see that there are only specific instruction or registers it works with. It can work with 2425, 2627, 2829, 30 and 31. What's the name of the 30 and 31 pair? Dante?
Would that be Z?
Right, that's the Z or the Z register, depending on where you're from. What would 28 be? 28 and 29. Mohammed?
That will be Y.
26 and 27. Basu?
That's a X.
X? Okay, how about 24 and 25? It doesn't have it. It just turns out that 24 and 25 can be used in this instruction, but there are no instructions which use a special case like these three are all usable in instructions. This is just a place where you can store a 20 or 16-bit number in the 24-25 pair. Okay, now, interestingly enough, notice that in encoding this, we have the opcode. We have the constant, which is only 6 bits long, which if we look up here tells us we can only add to it a constant which is from 0 to 63. So you can't use an 8-bit K here. It has to be only 6 bits. Additionally, notice the register can only be encoded in 2 bits. So what register would we be encoding for register 24? What would we encode down here? This will test your love of instruction coding. Well, if we have 2 bits, this can only be 0, 0, 0, 1, 1, 0, or 1, 1, which means 2, 4 is 0, 0, 2, 6 is 0, 1, 2, 8 is 1, 0, 3, 0 is 1, 1. Let that sink in a second, because there's going to be other instructions like that where you have to deduce what these characters or what these bits would be. And to do that, you really have to embrace the language. You have to really think about, if I were encoding this, how would I optimally be able to get the right number of bits into a 16-bit opcode? I could have made it a 32-bit opcode, but there'd been a lot of wasted space, even if I had had all the registers and this go all the way to 256 or 255. So that's an instruction that's available to us. It's very specialized. Don't be looking at that thinking you're going to be able to, oh, I can add register, 3 and 4 to something. You can't. It's very specialized. Now we have an equivalent set of subtract instructions. We have a subtract. We have subtract with carry. And then we have subtract with carry with the constant. We can guess that this is probably only going to work on 4 register pairs, and that the immediate part, the K part, is only going to be 6 bits long. But look here, we have another subtract instruction. Sub I. Let's look that guy up. Subtract immediate. We're going to subtract a constant away. Is this it? Nope, not there yet. Let me actually see if I can just find the first occurrence of it. Nope, not with that end. Where am I? I'm 15 out of 19. I keep going. There it is. Subtract immediate. Notice it can only use for registers 16 to 31. But the constant can be 8 bits. So if we're going to be only able to encode 16 to 31, and we have only 4 bits to do it in, what's the encoding for register 16? Scott?
0, 0, 0, 0.
Exactly. What would 31 be? Robert?
1, 1, 1, 1.
Yeah. Okay, so you guys are kind of catching on to how that could be encoded. Yeah.
I have one question about these opcodes. So we have 4 bits of K and then 4 bits of D and then the remaining 4 bits of K. Why do they break that up like that?
Because it lines up with the hardware finding this register in this place in some of their original instructions. Notice the opcode in this is only 4 bits long. In the last one, it was at least 8 bits long just to be the opcode.
Now, those Ks, are we assuming the ones that come first are the high?
That's the high. This is the low.
Okay.
You just read them left to right. Why in the heck do we have a sub I, but we don't have an add I? Remember, we looked at our program list back here? There's no add I instruction, but there is a sub I instruction. There's also a sub carry I instruction. Notice we have the same thing with subtract with carry. We have the I, but we don't have anything having to do with that with the add instruction. Why would that be? You're sitting around the table designing a CPU. You can only pick so many instructions. Why did they pick sub I but not add I? Robert, you want to take a shot at it?
I'm guessing that if you work with the 2's complement, you could use sub I to add I, but not the other way around.
Well, you could use either one to do either one. Mikhail, you have a comment?
Is it because the add instruction already does like the putting the result into the destination register part and all that?
Well, no. In this case, the answer winds up in the destination register. But all it is it's the source and destination are the same place. And all they do is they are bumped up with a number from 0 to 255. So, I mean, it would make perfect sense that instruction could be used. And it would be also makes perfect sense that if you needed an add I, as Robert said, we could just take the 2's complement and make it work. We could use this as an add I if we 2's complemented some things. But that's not the real reason why it's here. See if any of you guys would make good CPU designers, instruction set designers, architecture designers, trying to make you a lot of money. Well, I guess I'll tell you. I was hoping one of you would come forward with this. There's going to be another instruction we can almost bet, which is going to be called compare. How do you think compare works? Robert?
Probably subtracts in a constant to see if it hits 0.
Well, the regular compare will just do a regular subtraction. A subtract or a compare with carry will do just a regular subtraction. So if you wanted to compare something to a constant, a compare immediate would just do a subtract I. Now, the only difference is once it's done that, it throws the answer away. But since they had all the hardware already to do the compare in place, if they did a subtract I, why not build both? I mean, they could not tell you this instruction exists, but it does. because they needed this in order to complete the set of compare instructions they wanted to have. And the only difference is where it stores the answer when it's done. I thought a couple of you would get that one for sure. Some of you were pretty good. Robert, I think, came pretty close. Pretty close there. Okay, let's go back and take a look at what's next in our list. There's going to be a subtract with a word. We saw that. There's going to be the whole set of these with carry. And again, subtract with carry immediate. The only subtract immediate with the word, again, is going to look like this was a 16-bit entity. So if we go look at SPIW, what are we expecting to find? I wish they'd give me a way to click through on that one. They never do. Again, it's going to be in the set 2, 4, 2, 5, 2, 6, 7, 2, 8, 9, and 3, 0, and 3, 1. So, whoa. Am I back? Give me a green circle if you can hear me. Okay. I disappeared there for a second. Even on my own screen, I disappeared. Okay, so we have the same set of 8 registers here, pairs, 4 pairs. And again, the constant, we can only subtract away a 63. The constant that's stored, of course, will be a number which will have to be applied as its 2's complement. Because that's the way subtract works, right? Takes the second guy, 2's complements him, and subtracts him. So it's just minus that value. Okay. Uh-oh, I see flickering screens again. We'll see what happens here. We have and immediate, or immediate. We have exclusive or, but notice we don't have an exclusive or immediate. So just file that in your informational stuff. Let's pick one of these. Let's just say or. Okay, probably 1,000 ors in here. Well, we can take exclusive or since we're here. Full set of registers for both. Now let's find the real or. Complete set of registers. In the or immediate, only the top 16 registers can be used. So or immediate, even though it sounds like it's just the little brother of the other guy, has enough differences that he was probably adopted. Okay, he does the same function, but the register set, because we only have 4 bits to store it, they had to take only half. And it turns out the upper half is more useful than the lower half because it contains X, Y, and Z. And also, they knew already that people were using register 1 to contain a 0. There's nothing in the architecture, obviously, that supports that. It's just that C programming and C++ made that a thing that you just do. And so that's just the way it works. We have complement a register. We have take the 2's complement of a register. Don't be confused and think that means 2's complement. This means complement, means flip all the bits. This guy means take the 2's complement of the register. Now we have set bit and register and clear bit and register. Do these two instructions look like any two we have talked about before? Robert, which ones?
SBI and CBI.
Yeah, they look a little bit like that. One of the things is they're not that, and they don't even behave that way. In the case of both of these, they take a single bit or multiple bits to be set or cleared. They also aren't I/O instructions. They work only in the data space, meaning that if you're going to touch a register which is in the I/O space, you're going to have to, use the I/O address plus 20 in order to use them. But these hit the entire register. Again, a problem with that is, and anything that hits the entire register is, a bit could be changing asynchronously to you doing it. So you have to be a little bit careful about the registers you're working with. If it's something where individual bits can change, like an I/O register down in that first 32 bits or 32 bytes, you have instructions which could be individually bit addressable. In the data space, we don't have that. So although we can set a single bit with this, we're not really protecting the bits around it because the bits around it could be changing. However, if you look over here at what happens, the way they do it, we're going to take whatever's currently in the register and we're going to OR with it whatever the constant is. So because we're doing an OR, all the positions that have zeros in it will not be affected. But we are doing an OR on all the other bits at the same time. Notice here they're using the V-looking thing to indicate OR, and they're using a dot to indicate AND. So there are notations all over the place. In this case, if we're going to clear the bits, we subtract the bits we want away from FF, which means we get the ones complement of them. I'm sorry, the twos complement of them, which is what we want. And we OR that with it, and that with it, which will cause those bits to be cleared. Increment, decrement, do what you'd expect. I'm not going to look in the other book to see what registers you'd be needing to do that yourself. Here's an instruction, test. Test is going to check a register to see if it's 0 or negative. As a result, it's going to set either the 0, negative, or the V flags. And you look up the logic for setting the V flag separately. Clearing a register is done the smart way, which is you just exclusive OR it with itself. And again, we have an exclusive OR engine built in, right? We can do an exclusive OR. If the registers are the same, then we can clear the register. So it would be interesting to look up back here the exclusive OR instruction. I think it was back this way. No, it was EOR, isn't it? Here's the clear instruction. It's equivalent to doing an exclusive OR with both registers the same. Both of the things that we're going to be doing. So we should be able to look at this opcode. It's 001001. And if we find the exclusive OR instruction, Zero, zero, one, zero, zero, one. Notice how they've interlaced the R and the D register? Well, if you change all the R's to D's, this instruction and the other instruction are identical instructions. So literally, they're using exactly the same internal hardware to execute both of those. It just turns out that if you do it and the two registers are the same, when you're done, the thing will be cleared. So they gave us an opcode that reflects that. We also have one that'll let us set all the bits. And the thing I want to point out to you here, you have to look at a little bit, is when we clear the register, bits get set, flags get set. If we set the bits, it doesn't affect any of the flags. Beware of that. So although they have behavior, which is just different from each other, one turns them all on, one turns them all off, literally they have different behavior in terms of how they set the flags. That can bite many programmers up on the backside. So beware of that. Also set, S-E-R, well, S-E stands for set, R stands for register. Multiply, we're not going to talk about those. We just know they're there, and you in your leisure after the semester might want to browse through and see if you can make some multiplications work. There are some fractional multiply instructions, which is a special thing that needs to do to get some multiplication algorithms to work, and we have all of those. So this setup here was called the arithmetic and logic. We can almost hold all of those in our head. We then have branch instructions, and there's tons of these. We have something called a relative jump, and we have a jump. On this processor, they're identical. Although they're encoded separately, they do the same thing because we can reach every byte of memory using the K value that's stored in the instruction. If we use a regular jump, it takes a third register that our machine doesn't even have and adds it to it as well in order to be able to jump that entire distance. But since ours is only going to be stored into K anyway, then either one of those two instructions is proper. The better one to use, because it takes less t-states, is to use rjump when possible, just like using rcall instead of jump or call. There's also an indirect version of it where we jump to the address that's stored in the Z register, or we call at the address that's stored in the Z register. You have to know what you're doing to do those two instructions because you can really make a mess of things. They're part of what a language would call a computed goto or a computed call. Most languages have stricken that away from being inside the language because most programmers get into terrible trouble using them. But they're supported. And if we needed them, it's really nice to have them. So we have jumps, we have calls. And in association with the calls, we have two types of returns. The first return is a simple return that takes what's on the stack, restores it, and takes you back to the instruction after the place where you either made the R call or the call. The return I is returned from interrupt, or interrupt return, I believe they call it, which takes care of turning global interrupts back on. Remember when we had an interrupt, that's the same as a system call to the interrupt routine, but when that happened, interrupts were turned off so we couldn't have interrupts interrupting us. When we return back again, we want to make sure that interrupts are turned back on, but since we don't know where we're going to arrive back at inside our code because we were arbitrarily interrupted, we have the return we do take care of turning it back on for us. So the moment an interrupt is recognized, if we're going to service it, we turn off all interrupts. We then go to the vector that represents the interrupt we're servicing. We do the goto that's there, which sends us to the vectored interrupt that we're going to be processing. When we're finished, as long as we use a ret-i, we'll be returned to exactly where the interrupt occurred, and we will have interrupts re-enabled. So if another interrupt is ready to be processed, in most cases, we'll immediately go service the interrupt. However, depending on the processor we're using, we may have one instruction executed back at the previous site so that the interrupts can't swamp the machine. So we can make some progress in the non-interrupted code. Robert, do you have a question?
If we've set an interrupt and we use just routine, or sorry, just return, not interrupt return, would it still go back to the same place, just wouldn't enable the interrupts again? So if we were done
Yes.
listening, we would use return.
Yes, that would work. Okay, very unusual to do that, but that would work. Okay, now we have a bunch, well, just a handful, of compare and do something about it. The first one, we're going to compare two registers. If the registers are equal, we're going to skip over the next instruction. If they're not equal, we're going to execute the next instruction. Now, the next instruction might be a 1-byte or a 2-byte instruction, could even be a 3-byte instruction, but we're going to jump over the total instruction if we do a compare and we get an equal. You can imagine that the instruction after this might be a jump, a relative jump back to the loop in which this is ending. And you end when things are equal, for example. That's a use of CPSE. Now we have a compare and a compare with carry. Remember, they're just doing subtractions. So they're going to set flags, and the normal test you do afterwards tests to see whether the flag was set. These don't change the flow at all. They just set flags, as does compare immediate. And again, it's going to use the subtract immediate instruction, which we know only works on certain registers. So these are used to preset the flags if we have some instructions we need to do that don't set the flags before we want to reach a place where we test to see if we're going to do a branch. Now we have a handful of skip instructions. The first two work in data memory. The second two work in I/O memory. And as we recall, these two only work in the lowest 32 bits of I/O memory. When we're testing the port. So in the case here, we're testing registers. If the bit happens to be clear that we're testing, we give it a bit number. Then we skip the next instruction. If the key in the second one here, if the bit happens to be set, we skip the next instruction. And the same thing in the I/O ports. So here we're using a port number, not a register, because it's in I/O space. And as we remember, it's got to be one of those first 32 instructions, 00 to 1F in I/O space. Skip if clear, skip if set. Now we have more branch instructions than the dollar store can make money off of. All of these branch instructions check flags. And you take the branch if the flag is either set or cleared, depending on what you do with the instruction. Notice that we have these first two, which work only on the status flag itself, where we give the number of the status flag, and we have, look to see if it's cleared or set. Let's look at one of those in person. We'll use this one first. The branch of status flag is set. So it's a conditional branch. We're going to test a single bit in the S register. And if the bit is set, we're going to take the branch. Otherwise, we just go to the next statement that follows. Notice that the branch is a positive or negative number relative to where the program counter currently points. So if it's true, we're going to take the program counter plus or minus that value plus 1, of course, because it's advance it by 1 because it's a new instruction. Otherwise, it's simply the next instruction. And it pretty much works the way you'd expect it to when using symbolic labels. If you notice in here, the status bits are 0 to 7. 0 is on the right, and you'd have to look at the S register itself to see which bits that was. Well, we have a picture of it here. Bit 0 is carry, bit 1 is 0, bit 2 is negative, and so forth. We have our trap flag here, and we also have the interrupt flag that we can actually set to useful means with instructions, SEI or CLI, to set or clear whether interrupts can occur. But we can go specifically to those to decide whether or not we're going to do a branch. We also have every bit spelled out as its own instruction. So you might never use that, but certainly for a certain sense of symmetry, they added it. Over here, we can see that it's going to take 1 or 2 t-states to complete. Notice up here, by the way, that this is 1, 2, or 3 with these skip instructions, because it depends whether you're skipping and when you skip, whether you're skipping a single instruction or a 2-byte instruction, because that would matter. It's going to take longer to skip a 2-byte than it will be to skip a 1-byte. I shouldn't say byte, 1 word or 2 word. Scott, do you have a question?
Yeah, this kind of goes back to why we have a sub-I but not an add-I. So we're seeing instructions that kind of duplicate other instructions all over the place in here.
Absolutely, yes.
They really decided that, you know, these particular sets of duplication were more useful than an add-I instruction. I just find it surprising because add-I seems like it would be useful.
Yeah, but remember, add-I is very doable with the hardware for a sub-I by just making the second number of 2's complement of itself.
Fair enough.
So, no, I mean, the question you ask is one that they struggled a long time over, because adding an instruction to this hardware is a big deal. They've got to keep the speeds at which it runs down to most things completing in a single cycle. And so where they can reuse the internal hardware that does those 4 t-states we're not seeing on the screen here, or the 8 t-states, that hardware can be repurposed on a particular pipeline so that, oh yeah, all we're doing is taking 2's complement. That just means turn on an extra bit when you do the next t-state. And so that's a very good and very insightful question. Add-I is very useful, but I can bluff and simply use a sub-I with a 2's complement second operand, and I get the same result. And the sub-I is very useful in other instructions, whereas the add-I isn't.
Got it.
Okay, good. I'm glad you brought that up. That was very insightful. Not insightful like cause a riot, but insightful like in could see what's happening. Although I guess that could cause a riot. Okay, bits and bit tests. These two we love. They only work on a port, meaning they only work in the first 32 bits. And they can set or clear a particular bit. What's especially useful about those 2 instructions? Scott?
Kind of guessing here. Unlike any other instruction, they can operate on 1 bit at a time, so they won't be affected by asynchronous changes in the other bits in a register.
That's 100% correct, whether you're guessing or not. That is exactly the reason. They can read a bit or write a bit without having to worry about any of the other bits in the register in those first 32 bits of I/O space. If you notice, that's where we have all the ports, which are the things you want to do single bit at a time. Now, the only other place in the machine where that happens is in the status register, 3F in I/O space or 5F in data space. And it's abbreviated SREG here. Do we have any? Yeah, here's a couple. And we can set individual bits inside of it, and we can clear bits in there, or we can read bits in there that are independent of all the other bits that are going on. But these guys are very useful in the first 32 bits, which is where our ports live, and that's where we care about accidentally changing other bits. Almost always in the other bits, those things you're doing are either changed all at once anyway, or they don't mix read and write bits, or the data itself is 8 or 16 bits long. So these we want to keep and know that they exist. We could do the same thing with an SBD. What was SBC, I believe was, where were they? SBC and SBCI. We could do the same with these, where we just specify 1 bit. Oh, I'm sorry, that's to subtract. I'm reading the wrong thing here. SBRs, SBR and CBR. We could take a single bit, set or clear it, but we could accidentally wipe out the other bits. And if we were doing that in low memory space, that would just be simply a mistake. Logical shift left, logical shift right. It only shifts the 8 bits that were in the register, and the one that falls out just falls out on the end, like on the left end or on the right end. And when you're all done, if you've done it 8 times, your register would contain zeros. However, rotate rotates through carry, meaning it's a 9-bit rotate. When you go left, whatever was the left bit goes into carry. And whatever's in carry will come back in to bit 0. So we can manipulate carry between rotates in order to control what bits are going or coming. But we have, as you saw in the code I showed you last time, it allows us to set up multiple register shifts by shifting into and out of carry as we go right to left, byte by byte. And we can do the same thing in the right direction as opposed to the left. Whatever carry is gets brought in on the left side. Whatever is on the right side falls out into carry on the right. On the left side, it reads carry into the left or rightmost bit. Whatever's on the leftmost bit falls out into carry. We also have an arithmetic shift to the right. This one shifts to the right. The right bits are falling on the floor, but part of its operation duplicates whatever the left bit is. If you look over here, they're only shifting 6 of the bits, so that the sign bit gets propagated through the register. So if the number is negative, it stays negative. You keep rotating until you get all the bits on the floor. They'll either all be zeros or all be ones, depending on what the left bit was originally when you started the shift. There is no ASL. Why would that be? Scott?
There's no useful meaning to the bits that it would be pulling in from the right. They would just be zeros no matter what.
Right, so it's exactly the same as logical shift left. The instruction, which would be ASL, would be exactly the same as ASL. And here's a case where they did not give us an opcode to do it. Some compilers actually do. There are some compilers which, instead of 111 instructions, have like 113, where they've added some extra instructions to make up for the ones that could have been duplicated but weren't. But the hardware doesn't really support the idea of an ASL, because you notice here they're only really using 7 of the register, or 0 to 6 of the bits instead of 0 to 7 of the bits. So they couldn't just turn this hardware around the other direction. Swapping nibbles. Flag set, flag clear. Okay, my goodness, what in the world does this mean? You can come over here and read the results, and it gives you a big clue. Robert?
To me, that seems like it does the exact same thing as SBI and CBI.
except where is the S register?
Oh, right, exactly. So it's like SBI, only it works on the
Right. It
S-reg
works on
data
one
space.
special space, which is in 3F. Okay, instead of being in the correct spot, 0, 0 to 1F, that register happens to be outside the bounds. But you need to do it so often, they went ahead and gave you the ability to do it on that register. Because they have a whole bunch of instructions that can do it bit by bit as well. This is one of them. I take a register, I pull out this bit, and then I can change a bit inside of the S register called the T bit, basically doing what's called a bit store. I'm storing the one bit out of this register, and the place I'm storing it is inside the T bit in the S register. I also can retrieve it using bload. I take whatever T register has in it, I go to my destination register, and I set that bit on. So it's a way to transfer the bit. Remember, it's not saying set or clear. Whatever the bit is gets moved to T, and whatever T is gets moved to a register. So if I have a bit that I need and it's special, I have a special place to put it, but I can't just transfer it because of other bit activity. I can store it temporarily in the S register and then move it from the S register to where I need it. And since the S register can be taken, bit by bit instead of byte-wise, we can change a single bit easily that way. We can set carry, clear carry, set negative, clear negative. We've got every possible combination of how to set those bits in the register. We can even, clear or set the T register to be used with the store with the load up here later. So this gives us every possible way to set those. And in the case of all of these, it's a safe set. I can set clear and it won't affect anything else. I can set high, it won't affect anything else. Now, you can intuitively understand why it won't affect anything else. See if you can explain to me. That'd be a great test question. When we're using the S register the way we're using it, why don't I have to worry about the fact that it's not in the bit addressable range? Robert, what do you think?
Because the instruction is working directly with that bit and only that bit.
Well, it's even better than that. The reason is because there's no other instruction that could be executing that could have changed any other bit. Right? In the case where we have multiple things that could change while we're working with the bit, normally it's because some arbitrary piece of hardware has changed a bit inside of a register that we're writing to. And when we read it was 0, but now it's a 1. When we write it back, we wipe it out. In the case of this, while I'm setting or clearing carry, nobody else can be, because no other instruction could be executing except my instruction, and I only set that bit. So they didn't have to do a lot of hard work to make that happen. And the same thing with transferring the T bit. While they're doing it, no other bit could be being cleared or set, because we're the only thing running at that point. There's no multi-processing or anything going on. And this guy can't be interrupted by an interrupt, because that always happens at the end of instructions. Even if we recognize it early, we'll either throw what we did away or we'll finish the instruction and execute it. But we can't be interrupted partially through executing an instruction. Here's some data transfer. These are interesting ones because they're where we actually get data into and out of memory primarily. Everything else has kind of been working with the registers. Move is very handy. It allows us to move between registers where we're really making a copy. We also can copy a word. Let's look both those up to see what we can actually do with those. move lets us use any register to any other register in the register space. Notice here we're talking about 0 to 31, which is in data space, it is addresses 0 to 31, but you couldn't address it in data space. You have to address it as though it's a register. And then move W, which probably is next, allows you to move any pair. Notice it's always the even odd pairs. So 0 and 1, 2 and 3, 31, 32. So you can't misalign these with move word. You need to keep that in mind because move word comes into play once in a while when you're doing real programming. And again, they're put so that the second register is the high byte, first register is the low byte. So in the registers, data is stored in Little Endian when it's 16 bits long. That's unlike things like the SAP2 or the SAP3 or the 8088 where they were, while they're in the register, they were in Big Endian. So because we can map this registers into data space, and because data space requires Little Endian, the register that's mapped over the top of that is done in Little Endian. Now we come to more loads and stores again than Kmart might want to sell. We have load immediate, which takes a data place and loads it into a register. Now let's look at that because that isn't always what people are expecting. Let me It's going to load an 8-bit constant into one of those 16 registers. So again, the constant will be split with the registers here. So if we look at this, the data being immediate data is in the instruction itself, not in SRAM, unlike some of these which are dealing directly with SRAM. For example, LD comes in 4 varieties. It has, when we work on the X registers, 3 of those varieties. When we work on Y, it has all 4. And when we work on Z, it has all 4. The first 3 that all of them have is it simply does a load immediate, which we talked about load immediate. It goes to wherever the X register points, picks up 8 bits, and puts it in the register. It does the same thing, but when it's done, post increments X. So it can move X by 1. And it handles the carry between, for example, in the case of X, between the 2 registers, low and high, it handles that carry properly. You also can post decrement, meaning if you wanted to decrement the register before you use it, that's the other of the variety. In all 3 cases, X, Y, and Z can do all 3 of those. Y and Z have additionally something called the LD with displacement, or load indirect with displacement, where they take and use the Y register as it is, but add to it some displacement. So instead of going directly to Y, they go to some distance beyond Y. This is kind of like what we call direct addressing. And actually, we would have probably called this base relative direct when we were using our 8088 processor. So let's look at this guy. And Z has the same thing. It can use Z plus a displacement. It can't do any incrementing or decrementing in this case. And the opcode is different, but it exists. So let's go look at LDD. Probably right here. Load indirect from data space using Z. And now, let's see if we can figure out how to read this particular combination. Oh, yes, only the last one we're talking about. All they're filing the LDs under the same, because the opcodes are so similar. In our case, we're taking the register and we're adding to it a 5-bit, I'm sorry, it must be 6-bit piece of data. Now, this is interesting the way this is laid out. Look where Q is. Here is 1 bit. Here is 2 more bits. There is 3 more. So the 6 bits are distributed among the Ds. And the Ds, they have enough D here. They have 1, 2, 3, 4, 5. So they can, registers can be all 32 registers. Anybody have any questions about any of these loads? There'd be a page like this for the X's and for the Y's. The X would not have this last case, though. Everybody see how this is encoded? So also they've managed to wedge all that into 16 bits, which I think is pretty good. Okay. We then have an extremely useful one, LDS, where we do a direct load from SRAM. Now, LDS and LDI often get confused. Notice here RD and K, RD and K. What's the difference between the two RD and Ks that are written there? What do you see there, Robert?
So it looks like the K in LDS is actually a pointer to SRAM's.
I was talking simpler than that. Simpler, what's the difference between them? Well, one's uppercase, one's lowercase.
Oh, that too.
Yeah. And if we look in the data about how these are used, lowercase means that there's an address there. And so finish what you were saying.
So it looks like LDS takes the address stored in that K and pulls the data from the SRAM at that address.
Okay, let's look it up and make sure. Sounds like a good premise. So clearly we have tons of K, and we have a whole 16 bits to store it, meaning all of memory, I mean, a lot more than we have, can be represented in 16 bits. And what we're going to do is 0 to 65, 536. We never use a value that big because we don't have that much memory. And any register can be used. Program counters bumped by 2. We can imagine this thing probably going to run in 2 states instead of 1. Remember, we're AVRE, which means 2 states. Notice some of them have 3 states, and in one of the architectures, it's not even available. So there's times when you need to look here where you'll find some interesting information. So if somebody were to ask you how long this instruction took to execute, you'd take the 2 and multiply it times, because it takes 2 instruction states, which amounts to 2 T states, which are overlapped, in the pipeline, and you can multiply that times the time it takes to execute 1 T state, which on our machine is 1 over 16 million. Okay, notice here, no flags got changed in the S register. I don't think there's anything else interesting about that instruction other than it's a very heavily used instruction. And interestingly, why is this a heavily used instruction? Robert?
I'm just remembering back in the SAP 2 and 3 world that it was very time intensive to get data from RAM when you did a regular store, but this seems a lot faster.
Yeah. The truth of the matter is, on some of the older architectures, the only instructions you had were load accumulator and store accumulator, and everything else used registers. In our case, we have an LDS and we have an STS, somewhere down there, which are those two instructions. They're basically the only way you can get data from memory, except for all these other stores and loads that have been added to this machine to use pointer registers to make doing what this is more programmable. Now, we do have the load immediate, which is not one of those cases where we're touching memory that's in SRAM. Rather, it has the immediate data stored in the instruction. But all the rest of the stores and loads basically are our only way of getting to SRAM. And so they are the instructions we would normally use to make that sort of thing happen. You'll be very careful with this one. I don't want any of you catching anything. So what else we got here? We have 4 instructions you're probably not going to be using, which have to do with loading the program memory. And this guy here, which stores at program memory, which this guy is actually really a heavy-duty instruction. Amazingly, they don't even give you a count of number of cycles because it takes so long. It's used by the bootloader for storing data from the stuff that's coming in on the RS-232 line into program memory that you're going to be executing in the application space. Loading program in memory, we could use it if we chose to, but it's primarily used in order to initialize data. And we don't have to do it because we call a function, an old C function, I think it was called do copy data or something like that. And it does it for us. So we don't have to know how these 4 work. They're a little more complicated than we need to know about. We know about in and out. That's the ones that handle all of I/O space. And they don't do anything byte-wise, so they are bit-wise. So they're, when you can get a byte, use these, and they're in the I/O space. They're going to be fast and useful. We then have push and pop, which are instructions which are used on the stack. They always do 16-bit pushes and pops, so they take, extra T states to make that happen. But they're our way of saving data. So if we don't need to declare a full variable for it, we can save nested data, like nested calls can be saved on the stack. And they're used automatically by call and return, and return from interrupt to do the right things for us. We have 4 more. The only one of which we might ever use is no-op. If we were really running on a machine where we wanted to save battery power, we'd use sleep a lot. If we worried about runaway programs, we'd use the watchdog timer, but I'm pretty sure the way the fuses on our 18 megas have been set, we can't use it anyway. And break is used if you're writing a debugger. I don't think we're to that point yet. But the one we might use out of these control set would be no-op, and we usually use it to kill time. We had to delay for a cycle, we could throw a no-op in. And mostly used to finely trim anything we're doing in I/O where we need a waveform and we need it to be down to the cycle time. We might throw in extra no-ops to get exactly the timing we need. As a way, if you had a delay you needed, but you only needed to delay some very few number of picoseconds or nano, well, in this machine, nanoseconds, we could use it. And that is the instruction set with a tour of what we would need to do. Anybody have any question about any of those things we just talked about? During the exam, you will have this document and that document available to you. So you don't have to memorize them, but when you're programming, you can program a lot faster if you can expect them to be there. Like if I'm going to write a program that has increment in it, I'm always going to have to look up in here what the opcode for increment is. Okay, on this machine, it's INC. Decrement's DEC, because I know it as INR and DCR, other names for it on different machines. So I will look it up unless I've been working recently on this machine and just happen to remember. I'll probably spell exclusive OR wrong the first 15 times I use it on this machine, because here it's EOR, not XOR. I will probably forget that there's no XOR immediate and have to, come up with a workaround for that. But with this, I can, see how it works, and I can look up what registers. I might write an instruction and try to use register 8 on an instruction that can only be used with 16 to 31. And I'll have to rewrite my code or work on my code to make it work. But that's why they pay the assembly programmers the big money, is because they can adapt and can move from machine to machine. And once you've learned one like this and you can very thoroughly make your processor do what you need it to do, you're a very valuable asset. Remember, knowing the AT megas ins and outs lets you design anything. That LED, I don't guess many of you have realized this yet, but if you treat that LED that we can turn on and off as simply a digital output that I can attach to the world, anywhere the world has a digital input or output, and I can turn it on or off, or I can read it, I can control the world from this board. And that's very significant. We know enough hardware-wise that we could hook up to many, many different types of sensors, and we could be able to monitor the world using, the Arduino processing combo on our PCs. We can also, with processing, command it to do things. And using output pins that we can't attach to now because we don't have the hardware, but we already know how to do it because we talked about it earlier in the semester. We could, control the coffee maker. We could launch the missile. We could cause the windows to go down on our car. We could detect the fact that our car just ran into something and automatically, send out a phone message. So there are all sorts of things we could do, and by being an assembly programmer, we're able to make it work and make it happen. Yeah, we could come back and rewrite it in C so it's easier for simpler people to maintain, but by knowing how to do this, we can get a lot of code on a very small processor, where some processors you couldn't even run C on them because they don't have enough memory. Okay, let's look at encoding something for a second here and see if we would know how to do it. Let's take something simple, because this could be something you would be asked to do. What if somebody asked us to encode that instruction right there? Let's encode ASR register 19. First of all, think about what the instruction does. Let's assume for a second the register contains that value. After our instruction, what will it contain? Somebody answer that question, please. Scott?
110000101.
Okay, so what it did is it took these registers, this one, that are here, and it moved them there. which means this one got lost. So it just went out and fell into the bit bucket. It then took the leftmost bit, which was in our case a 1, we'll call it a Z, and it duplicated it. Okay, which got rid of that X. Okay, now I lost an X here somewhere. I guess it's the one I just deleted. I should have pushed over. So really what it's doing is it's duplicating the left bit, which pushes all the others over, dropping one off on the right-hand side. So if this had been a 0, then it would have pushed into the first two positions a 0. So we'll put back what he had. We would duplicate that. We still have the 3 zeros. We have the 101, and the O fell out the end. If it had been a 0 there, we would have taken and duplicated the first guy, and we'd have put the 3 zeros, then the 101. And of course, the 0 in the end would have fallen out. So it always keeps it either positive or negative, depending on what the left bit is. So we're still looking to encode it. We need to look at the documentation. So we're looking up ASR. We'll see if it's easy to find. Can't believe there's more than one ASR in there. Oh, there's not. So it can be any register, so we know it's a valid register. Don't be tricked by that. You could get one where you couldn't encode it because of the fact that this register was 16 to 31, and we coded 19 or something. I don't remember what we coded. But this guy right here, see if that can be copy-pasted. And we would put it in a row all by itself here. Says the only thing we have to encode is the register. So getting rid of all of this because we don't need it. We need register 19. 19, we have to write it using 5 bits. 5 bits means we have a 32, we have a, I'm sorry, 16, we have an 8, a 4, a 2, and a 1. So what value would we have to write in order to get 19 out of these? We need to have the 16-bit turned on. We need the 3-bit and the 1-bit, or 2-bit and the 1-bit. We need 3. 3 plus 16 is 19. So that means this is a 1. This is a 0, 0, 1, 1. And if we group those together, that becomes a 9. Second number is a 5. 3. And a 5. So what is 9535? What does it stand for? Oh, Scott, I see you're still here. Nobody else seems to be here tonight. What is that?
This is the encoding of just the opcode piece.
Actually, it's all of it.
Oh,
It's the whole thing. Because embedded in here, in the D field, is the register. We know that that's the D because that's the register that's here. Let's do another one. Go back over here, find one we love, know and love. Let's do LDS register 17. Where'd I go? I lost my window. Try to encode that guy. When you get it encoded, turn your green light on. Hey, Andrew, what did you think the answer is here? What should I encode?
1001.
1001?
Yep.
Is that binary or is it that hex?
Binary.
Okay, well, I need 16, need more digits.
0001. 0001.
Again. Well,
0000.
okay, well, we'll look to see. Did anybody else get the same answer he got? Your microphone, by the way, Andrew, is making some really strange sounds.
Oh, sorry.
I don't think it's your fault. I think the mic, it sounds like electrical. Maybe the plug isn't in all the way or loose. Okay, well, let's work through and see if there's any issues with this. So we'll go, first of all, pull out of the document, the LDS command, just be consistent here. We're not the RC model, so we'll take this guy here. Okay. So there's our 32 bits we need for the instruction. Now what we need to do is we need to think about encoding it. We have 5 bits for the register. Were there any restrictions on the register? Well, it looks like we can use any register we want. We're using register 17. So he's proposing that that's 10001. Replaces that. Okay, 16 plus 1 is 17. Okay, now we have the value where we're going to go to get the data. Now, if we strictly take that as this being a hexadecimal number, we're going to have 1, 2, 3, 4. And this will turn into hex, and that'll be our instruction. Turn that into hex, then somebody tell me what it is. Dante?
It would be 9110, then just 1, 2, 3, 4.
Yeah. Now, I'm going to have to check for you whether or not this is ever written in Little Indian. I would always code it this way because something struck me right now about one of the machines that AM or that Atmega made, or Atmel, I'm saying the wrong words, Atmel made, and they did flip the bits here. In our case, we're going to leave it as K being straight through, and that'll be our convention unless I tell you otherwise. But this would be the answer to that. Now, if I gave you that and said, tell me what this instruction is, how would you approach that? Dante?
So this will kind of be me working through it as I'm explaining it. But so first, I can immediately tell it's going to be something that has 32 bits. So I know it's going to be a 32-bit opcode. So
How would you know it had 32 bits?
Because it's
What if this had some other numbers following it? I said, tell me what the current instruction is.
And at that point,
That could be a problem. Oops,
Yeah.
whoa. We'll get that back.
yeah, at that point, I wouldn't be too sure how to do it.
What key did I possibly hit? There we go. Yeah, well, no, what you said is if you're given it this way and it's divided down, that's one of the things we could do.
So I guess I guess we just do it the same way we did the last ones, where we just break it into groups of 4, and then from there, you can try to translate the 9110 into the register. So you could get you could try to just basically convert it into a binary opcode, and then from there you just check your opcodes to know what it is.
Okay, very good.
By using
You hit exactly on the problem, though. If you check the opcode for this is all of that, well, except for the D. Did you notice in some of the other instructions the opcode's a different length? It turns out that if you were to build a tree, for those of you that are data structure oriented, you can build a tree of the opcodes. Some are very short, some are much, much longer. Some of them have zeros where in their other instruction state, it's actually really a value, but they've encoded register 0 in that position. So to be honest with you, it would be a very unfair question for me to ask you to take something that's encoded like this and turn it back into the instruction that generated. So I will not be asking you that particular question. I will ask you the other direction, which is I'll give you this and you tell me what this is, this, but I'm not going to give you this and ask you to get back to the original instruction, at least for the ATmega 328P. I will for the 8088 because we know how to do that. And he was right on target with what you would do in order to do this. It's just you don't have a table of all the opcodes. And the table is not easy to use because the length of the opcodes changes. It actually did on the 8088, but we stuck to one instruction who always had a 6-bit opcode. So that would be an unfair question. Now, in more important news is, why is this an invalid instruction? Nikhil?
Is it because it's not in Little Indian?
No. Remember, we're going to assume that any instruction will be written as though it's just in this order in memory. Okay. If it's not, we'd worry about that as a different exercise. Anybody have any ideas on what's wrong with that instruction? Dante, what do you think?
It's going to sound dumb if it's wrong, but is it because LDS is directly from SRAM and SRAM isn't register 17?
Say what you said again. What's the last sentence you said?
It's SRAM isn't in the SRAM doesn't have a register 17 or register
No,
17.
that was. Oh, you're so close. You are so close. It's not register 17 we're worried about. Let me just write something on here that may or may not have any effect on this equation. I'll just write that to remember it till later, in case somebody ever wants to mention it. Scott, do you have a comment?
It's because the highest address in SRAM is 08FF,
And what address are we using?
1234.
Because that's illegal, isn't it?
Yep.
So the biggest address we could have in this instruction and be a valid instruction is 08FF. Now you might say, well, what would happen if we executed this? Well, let me answer that by saying something would happen. It probably does a mod of the amount of memory you have when it goes after this unaddressable memory, and probably throws away the bits we don't need. So it probably somehow maps this into this range, but why write it wrong? This is the correct instruction. Scott, do you have another question or comment?
I got a couple actually.
Okay.
So the 1234 that we provided here, if we don't prefix that parameter with a 0x or anything else, it'll be presumed.
This would be in decimal if you're writing it. I just said when I typed it, I said I'm writing in hex now. To be proper, that should say that.
Oh, okay. And my other question, just thinking back to the Intel format where you had checksums and other parts of the encoding, we don't have any of that in this chip, right?
Oh yeah, we create the same file. You know, actually, since everybody else seems asleep, that means their board is just you and me and a couple other people. Let's look and let's do the technical analysis of this. You know, we're up for it. Let me see if I got a window here where I kept any of that stuff available. It's this guy. Yeah, I actually did. See, you guys don't think I didn't know what I'm doing, but I do. Sometimes. Okay, let's first of all CD into app data local. Whoops, not that guy. Arduino build doesn't exist right now. Okay, so I have to open Arduino for just a second here. What I'm going to do, I'm going to go look in that folder. We'll look at how it compiled, and we'll see whether or not it's big indent or little indent. Doesn't that sound like a great adventure? I can find my labs folder. Okay, give me a green circle if you can hear me. I swapped a whole bunch of windows around there. Okay, so where were we? We were in this window, and we were trying to find Arduino builds. Okay. So what we need to say, let me see what's in this folder. Just to answer your question earlier about all the checksums and stuff, if I do a notepad on lab9.ino.hex, there's all our friends. Remember those guys? It starts with a semicolon. We have a length field of 16. We have the starting address, types of records, all that sort of stuff. It's all here, and the checksum sits at the end. But what I was going to do is, let me see if I can rebuild this. This is called Lab 9 something. There you go. Copy. You guys know how to build these. You'll be doing it on your finals, so you better know how. Okay, well, we can determine without going much further than this by simply looking at what's here. Okay. Our processor is doing little indent. So if we take this, call this a valid instruction for the moment. If you were asked to put this into little endian, you break it into two parts because it looks like it's just doing instruction little endian. So the actual way this would be represented in memory would be 1091 FF08. If we looked in memory, this is the way the instruction is stored. Now let's see if we can figure out how I knew that. Look at one of these lines. This is the instruction. This is coded generated. So how did I know things are stored in little endian? And it's word-wise. Every 16 bits are in little endian, not every 32 bits, every 16 bits. Somebody take a shot at this. Leslie, what do you think?
So it is in Little Indian because the format before it has like 9110 and after it has like the thing we got is 1091 and the same thing like
No,
yeah.
no, we're talking about over here. How do I know this instruction, when it's encoded, is those values in little, these are in little endian? Scott, do you want to take a shot?
The address we're jumping to in that first line is different from all the others. And if you look at the encoding, the part that's different is the 34 versus the 51. So that suggests to me that it's little endian. Those would be the lowest bits in the word. That would be different.
Yeah, you're very right about that. This is a little endian number, but wait a minute, it doesn't match this number. Or does it? What if I told you these are bytes? Aren't addresses actually words? Meaning that the number of bytes would be twice the number of words we needed? Wouldn't it be cool if 3.4 was half of 6.8? So this is word number 3.4 in hex, which is the same as byte number 6.8. And yes, it's in the left part of that, which implies this is the high bits, that's the low bits. So what we now have to prove is that 940C looks like a jump instruction. So let's write 940C. And let's look in our book here and find the jump instruction. So here's what we need for the first byte. Well, let's put it. Nope, I'm still at the wrong window. There we go. So we want 940C. So it'd be nice if this line and this line could match in some way. Okay. Well, we have a bunch of K's in here. What would they be? Well, the address we're jumping to, we said we only have 14 bits, right? So 8, 9, 10, 11, 12, 13, 14. There's the high border bits. But our address is way below that, meaning all of these really are zeros. It'd be really cool if that matched that. Well, it looks like they do. And since in memory it's written in the other order, meaning the 9 comes in the second part, and this is the Charlie part, then this is little endian. So there's the little endian first part of the instruction. There's the little endian second part of the instruction. Eventually you get down to, here's some instructions that are only 18, but if we look this up, this is going to be the exclusive OR part, and this is register 1 and register 1. Even though that looks like that, we'd have to find the bits to be precise. So that was pretty cool. How was that for a side adventure? Do you all feel like you've been spelunking? Now, who wouldn't enjoy doing that? Okay, let's get rid of that for a second. Get rid of that for a second. Go to your labs folder. Right-click on Lab 0. Make a copy of it. And just paste it into this folder. rename the copy to be Lab 9. And then go into the Lab 9 folder and change the INO folder to be lab9.ino. And let's open that up. And give me a green circle when you got that part done. Okay, I think I got all the windows I don't need closed. Okay, what we want to do is we want to write something that we could use on the test if we needed it to help ourselves out. Go to the code, make sure we set it to output, and then we clear it. There, you might have a set there, but make it a clear. Okay, now open up a couple lines there. Line all by itself. Let's load immediate into register 16 a hex 32. Actually, let's make it not be a hex 32. Let's pick a number that's a little odder than that. Let's put in the number 123 in decimal. Now we know that we should be able to do an R call to the function we have that knows how to print a character, or I'm sorry, to go to hex. It's not, well, what did we call that thing? It's in the utility function. I believe it was just called 2hex. We'll know when we compile. So register 16 is passed in. I'm actually going to use lowercase on my register, just more comfortable to my eyes. Then when we come back, register 16 contains the left nibble turned into hex and the right nibble turned into hex in register 17. So I should just directly be able to R call the other register, or the thing usart send. And then if I transfer into register 16, whatever's in register 17, and call it again, I should print out the second number. Let's first of all see if that compiles, see if I've made any typos. Now make sure that your Arduino is plugged into your USB port. Make sure you don't have processing open anywhere. And just hit the load button. It should recompile what needs to be compiled and load the rest of it. Okay, mine looks like it ran and loaded. Now, if you open up the serial monitor, either Tools, Serial Monitor, or Control-Shift-M, depending on what you wish to do, we should see the number 7B printed. So that's 7 times 16 plus 11, which should be 123. So we have the way to verify a register by simply loading it into 16, then doing this little dance here to print it out. If I did it a second time, I'm just going to call this a second time. So copy and paste it. I have it in here twice. And the second time, I'm just going to put in the number, I don't know, 46. And run it again. It probably will compile, so I'm just going to hit it and let it break the compile and not load if necessary. Now we have a little problem in that it's printing the number back to back and knowing where the lines separate and all that. That could be bothersome to try to figure out. So what we could do is we could load a new line character into register 16. So move immediate to register 16 of a new line and call the send again. So I could copy those two lines again. I could paste them here. Now I should be able to run. Let me actually come over here first. I'm going to hit the clear button just to clear my output. Then I'm going to reload this. Oh, I have an error compiling. What the heck did I do wrong? Who else besides Dante sees what I did wrong? Dante, what is it?
We don't have MVI in this for the Arduino.
So what instruction should I be using?
We'd have to do.
I'll click on a line that's similar.
Load immediately. With
Yeah, let's do a load immediate, LDI. That could be a bug that has to be fixed on an exam or something, right? Now we'll load. Okay, clear it again because I had something on my screen. What I'm going to do, I'm going to go over and push the reset button. It'll run again. Should print out the two numbers on separate lines, which could be useful for us to have. But I'm starting to see quite a bit of debugging code having to be presented here every time I want to use this print function. So if I had a program and I wanted to instrument it with lots of plays to debug things, it starts to look to me like this code is repeated with no difference. I don't see any difference in this code. The only thing being what I loaded into 16 beforehand. How would we approach, what do you think we should do? What would be a reasonable design thing to do if we started to see that happen? Robert, what would you suggest?
I would suggest after the LDI, but before the R call to hex, let's just make a label so that we can call it multiple times. And it will just depend on what's in register 16 when we call that method.
Okay, so what you're telling me is I don't need the second one.
Correct.
I could take the first one, move it somewhere else, and make a subroutine out of it.
Correct.
Okay, so let's put it here. And let's give it a label. Let me, I picked a label earlier, print it. And of course, it'd have to have a return at the end. And then in each of these cases here, we could do an R call, print it. Which seems like that would save a lot of trouble. Let's see if that compiles, and if not, what errors did we make? Try to load it. Okay, Rotu, now I'm going to clear it again and run it with a reset button just to make sure. Okay. Now let's think about it as designers for a couple minutes. Does our subroutine need any beefing up? Robert, what would you say?
The only thing I could think of is maybe we want to check and make sure that there's something in R16.
Well, there'll be something there. I mean, it may not be ASCII, but that's okay because remember, we're turning it to hex. And when we turn it to hex, we're turning it to 2 ASCII digits. So there's no way we can put anything in register 16 that wouldn't be printable as 2 ASCII digits.
We might also want to make it able to display a whole byte or a word instead of a whole byte.
I would say that we probably don't want print it to do that. We might have another function which we call print it twice. I think the idea of being able to print a byte is something that's useful. Scott, you had your hand up there for a minute? Oh, it's still up.
Yeah, we should push the contents of R16 onto the stack temporarily before we do our move from 17 into 16.
Okay, let's think through that for a second.
Or well, something to that effect.
Okay, so let's push register 16 here. Now we use what's in 16 to turn to hex, which after that, 16 contains an ASCII character, 17 contains the right half. So the left half and the right half ASCII characters are available. If we this uses 16 to do the printing. So we can take what's in 17, move it to 16 and print it again. We can wipe out 16. At the end, it didn't matter that we save this because all we're going to do is pop and return it. Oops. But there is one valuable thing to that. What that tells us is a user of us knows that when they get back register 16, it's exactly what they sent us. Because in our case, it wouldn't be. It would be a new line. Or whatever this routine here did to change register 16. What we do know is this guy, we can look at him. He only touches register 16, so there's no bad mojos going on with him causing any other problems. But we want to make sure the guy that called us, as long as we document our function to return the same thing, which if we're using this for debugging, we probably want to know if we put a 46 in it and call print it, when we come back, 46 is still in R16. So the push is correct here, the pop is correct there. Another thing is, did you notice this guy destroys 17? He's using 17 to receive the results of 2 hex. So it would also be wise to push our 17 onto the stack and restore it down here. Now, if we run this, things are still working, which is good. We didn't really bust anything, but we've protected both 16 and 17. So the guy that called this knows that whatever he put in 16 to be worked on and whatever was in 17 is still intact. There's one other thing we might want to think about. what would that be? Put your designer helmet on. And well, I think the Jeopardy tune to myself here. See if you can think what it would be. Well, how about this? What happens if the guy that called us got register 16 loaded with a number with an instruction that also set clear or set 0 or one of those flags? When he came back, wouldn't he expect those flags still to be set? Are we guaranteeing that we're not changing any flags down here? I'm not guaranteeing it. So it's probably be a good idea to save the flags. Where are the flags located? Scott?
Status register.
Yeah, where is the status register? It's an IO space, right? Yeah, but it's not one of those that you can use those short instructions on, but we can still use the in and out instructions. So if we think about it, we're actually doing it down here. We're saving it, right? In an interrupt. So why don't we do this same thing here, right? We can grab it. And we can push it on the stack. But you know what? Let's not use register 2 because then we're going to have to worry about saving register 2 also. Let's instead, since 17's been saved, let's clobber 17 with it and push that on the stack. We have to use an in, but that means right here before we restore the real 17, we should be able to get it back again. And so what we would do is we would pop register 17 and we would output it to the special function register. I'm just going to copy the output instruction we have down here. Of course, using register 17. Now if we run, it should still work, meaning we didn't save things in the wrong order anywhere. But we've managed to preserve register 16, preserve register 17, and preserve the status register so that the person calling us doesn't have any surprises when they come back from their function. So if we had something in here that said, let's take register 16 and let's do an and on it. Actually, is that the correct instruction name? Let's and register 16 with a 0x22. Now when we call print, let's call them one more time here. Register 16 should still be intact. And I'm going to clear that and run it with this reset button so we only have it printed on there one time. Okay, we have a 7B. We ended it with a 2-2, and it says we have a 2-2 in the register afterwards. Is that the case? in here. Seven. B. 2. 2. Handing those together. 0, 0, 1, 0. 0, 0, 1, 0. We seem to have 2, 2. But we were able then to not only deduce what it is, but we can actually look at what the register changed with. I could imagine that being extremely useful to have a tool that you could use that and actually test out instructions with it. Anybody have any other questions or anything about what we've been looking at? Okay, so proclamation that when we have to write the encoded version of an instruction, we will use 16-bit little endian. Since we discovered that by going on our adventure tonight down into the cave. And everybody is aware of when the final exam is. It's Monday, the whatever that says on Blackboard. Next week, we're going to work on some code and review some of the things we've done with the Arduino. I shouldn't say the Arduino, with the AT Mega. And then on Wednesday next week, we'll do a full, pretty robust review of things you might have forgotten in order to be prepared for the final exam. Does anybody have any questions? Okay, well, I hope you all had an immense amount of fun tonight. I certainly did. I will see you guys on Monday, I guess. You all have a nice weekend. Don't forget your homework, by the way. You're going to owe me that processing program that does the meter, the bar graph thing, on Monday at the start of class time. So good night.
Good night, Professor.
Good night, Professor.
Good night,
Good night.
Professor. Good night.
Bye-bye. You all have a good
Good night,
one.
Professor.